Okay, so now we look at torque. And we will look at torque again in the next chapter, where we will see it in a sort of a more as a form of a vector. But now we'll just see what we mean by torque. So it's like in linear motion we have force. So in rotational motion the equivalent of force is the torque. So if we consider a wrench or a spanner, and we have a nut over here, and we want to open this nut, so we apply a force over here, and that will cause this to start turning. So what we are applying is a force over this distance. Now if we apply the same force here, you would intuitively feel that the same force applied here will not create that much of a twist at the bolt. So if the bolt is real tight and you apply the force here, the same force as you were applying here, if you applied it here, it might not be able to open the bolt. So the further away you go, the bigger is the effect of that force over here. And that effect, or that turning force, is the torque. So the torque, which we write as a tau, okay, it's a Greek letter, that torque depends on how far away that force is applied. The further away the force is applied, the bigger becomes the torque. And so the torque is a force times a distance. And the units of force is Newton, unit of distance is meter, so the units of torque become a Newton meter. In the American customary system, it's a pound foot, so it's called a foot pound instead of pound foot. Now let's go a little further. Suppose that we are applying the force at this position so that we get the maximum torque, but we apply the force in this direction, and now we would see that it's not going to cause the spanner to turn, and the bolt will not be opened because the force is not going to create any torque. It's just going to push it inwards, and there's no real twist. So it's not just the force and the distance, but we also have to see the angle. Now if we see this again here, let's say instead of applying the force perpendicular to this distance or parallel to it, we apply the force at some angle. Now what would be the torque? And this distance from here to here, let's write it right here, this is R. Then this is the direction of R, and that's the force. We can break the force up into two components. One component along here, let's say that's the x direction, so this is Fx, and if that's the y direction, we would have an Fy. The Fx would not cause any twist, it's just going to pull the wrench outwards, and if it were pointing in, it's just going to be just like this one, pushing it in. There's no twist. So Fx creates no torque. It's the Fy that creates the entire torque. And so the torque is going to be Fy times the distance. So the magnitude of the torque is just Fy times distance. And let's write it once again. The magnitude of the torque is going to be Fy. If that angle is theta, the angle between R is going to be in this direction, and theta, and F, so that's theta. So it's going to be F sine theta R. Or we can write it as Fr sine theta. And since you've done the cross product, you would know that this is R cross F. Well, the magnitude of R cross F is Rf sine theta or Fr sine theta. In terms of numbers, it doesn't matter whether you write it R first or F first. Now r cross f is a vector, so the torque is a vector, and the direction of r cross f is perpendicular to the direction of r and also to f. So in this figure we have x and y in this plane of the paper. The z-axis is coming out of paper. Then the direction of torque is in the k direction, and we will have the torque is the magnitude of the torque in the k direction in this case. Well, if the force were pulling downwards, it would be in the negative k direction. So that's the direction of the torque. Now, one thing more about the units. Even though it's Newton meters and Newton meters are joules, torque is not written as a joule because we reserve the joule for work or energy. And even though it's Newton meter, the Newton meter is reserved for torque. Now let's say that if you apply a torque, what happens to the object? So if we consider let's say a light rod, and there's a hole in the pin in here, and we have a mass over here. So this thing has a very little mass and we're going to ignore it, but it's a rigid rod. And if we pull it with a force perpendicular to the rod, this is going to go in a circular path. Now the mass of this is m. Now we know that F equals ma. So this force is going to create an acceleration in the mass in the direction perpendicular to the rod. It's just going to move this way. Now A would be the tangential acceleration. There would also be a centripetal, but this force is going to create a tangential acceleration. Now we know that A or AT is R alpha. So we substitute that here and we say F equals m R alpha. Now when the force is applied here, there's a certain torque acting at this point. By the way, this torque will act at that point. So the axis of rotation is important here. Sometimes it's not, but here it is. So if you want to find the torque that this force exerts at this point, it's going to be Rf sine theta, and the theta between the R and F is 90 degrees, so sine theta is 1, so it's simply Rf. So the torque is going to be Rf, and F is mr alpha. So the r squares can be combined together. We get mr squared alpha. And this is the equation that we were looking for, that the torque equals mr squared alpha. This combination we call the moment of inertia. And we write it as a capital I. So for a point mass, the moment of inertia equals mr squared, where r is the, let's say, shortest distance between the mass and the axis of rotation. So in this case, the axis of rotation is here, perpendicular to the paper. So this is the r. If it were rotating about some other point, then we would take a different r. So it's the distance, the perpendicular distance, or the shortest distance between the mass and the axis of rotation becomes mr squared, and the units become, units of mass is kilogram, units of r is meter, it becomes kilogram meter squared. And so we write mr square as I, and so the torque becomes I alpha. And this could be similar to the second law in linear motion. So just to rewrite them here, in linear motion, the sum of forces is ma, and in rotational, the sum of the torques equals I alpha. And we say sum because there may be more than one force. There may be one force here, there may be another force pulling in some other direction which creates its own torque, and there may be a number of forces creating their own torques. So the sum of all the torques is I alpha, and they're both vectors and they both have the same direction. So as it accelerates, the linear acceleration, the tangential acceleration is in this direction, but the alpha is perpendicular to it.